We're going to look at another fundamental design technique which can be applied to a variety of problems called dynamic programming. Now, rather than getting into the nitty-gritty details of what it is first, we're going to look at a motivating example called matrix chain product and then extract from this how we tackle this problem specifically using dynamic programming, so what the common elements of dynamic programming are, and then use that in order to apply it to another problem, the 0-1 knapsack problem. So first we're going to get into matrix chain product and what that is. Now, in order to do that, let me go back for a moment and review a little bit of matrix multiplication. This was kind of the last video of what we talked about, and that's multiplying two matrices together. Now, matrices actually come up quite a bit. These are useful as subroutines for a variety of problems, including if we want to use them in order to solve or represent a system of linear equations, we can use matrices to do that. This is also used in game development, so it can represent calculations related to position or motion or rendering. And matrices are also very useful to represent distances in a graph, and so they'll appear in a large number of graph problems as well. So let's do a quick kind of refresher on how to multiply just two matrices together. So we've got some matrix A, which is a D by E matrix, meaning it has D number of rows and E columns. And we've got a matrix B, which is an E by F matrix, meaning matrix B has E rows and F columns. Now when we multiply those together, definitely in order to even be able to multiply them together, we need to have that these dimensions are the same. And then our resulting matrix is some matrix C, which is a D by F matrix. Now how we calculate this, this is just given by each cell in the matrix C that we're going to come up with. The value at that cell is determined by the summation of the product of each element in A and each element in B at that specific row and column. So for example, if we had here is A1 all the way up until AE, each cell from the first cell here to the E'th cell at specifically row I. And here in B we had B1, B2, B3 all the way up until BE in column J. Then in our matrix C we would compute what we should store at that cell at row I, column J. This would be the summation of each of those values, which is A1, B1 plus A2, B2 plus each one of those corresponding cells multiplied together added to the product of the next cells multiplied together all the way up until AE times BE. So the total running time of this is big O of D times E times F, where D is the number of rows in A, E is the number of columns in A, which is the same as the number of rows in B, and F is the number of columns in B. So our total running time is big O of D times E times F, a product of the dimensions of A and B. Now, if we had two n by n matrices, this already gets to be pretty expensive. If we had just A and B are n by n matrices, then we would get an n cubed running time. And I talked about how we could improve this a little bit in the previous videos, but that we still don't have a way to get this to be close to n squared. So if we had to multiply not just two matrices together, but a lot of matrices together, this would turn into a very expensive operation. So this is what the matrix chain product tries to help with. So we have a chain of matrices that we want to find the product of. So we've got n matrices that we want to multiply all of them together. So we've got A0 times A1 times A2 up till A sub n minus 1. Now each matrix has a different dimension associated with it. So we have A0 is a, let's say D0, this is the dimensions, D0 by D1 matrix. A1 is a D1 by D2 matrix, and AN-1 is a Dn-1 by Dn matrix. Now if the dimensions of all matrices were n by n, then we would have, since multiplying two n by n matrices together, we could do that in big O n cubed time. To multiply n of them together would already be big O of n to the fourth power. Maybe we could do a little bit better, but no better than n to the third power, just using the techniques we've seen before, which is already very expensive. And our goal here with the matrix chain product actually isn't to multiply all of these matrices together, but it's how do we figure out the best way to parenthesize this so that we have the correct order in which we should multiply matrices together. And by order, I mean specifically that we have some parenthesization so that we know, okay, that if these are parenthesized, then we'll first multiply A0 times A1, and then we'll take the result of that and we'll multiply it with A2. And then maybe we do some other operations and then we take the result of that and multiply it with this larger matrix. So the matrix chain product problem is that we want to, given a chain of matrices with different dimensions, figure out a way in which we can parenthesize them so that we minimize the total number of scalar operations that we have to complete. And the scalar operations are just based on, we're given two matrices. Let's say this is, like we had in the previous slide, this is a D by E matrix, and B is an E by F matrix. The number of scalar operations we need in order to multiply these two matrices is big O of the product of the dimensions of those matrices. So these scalar multiplications and additions, this is just coming from, in order to multiply these two matrices, we have to multiply different cells in each of these matrices and then add those results together. So this is the number of scalar operations that we perform when multiplying just two matrices together. So we want to minimize the number of scalar operations. So for example, we've got, let's say we've got these three matrices, B, C, and D, and they each have different dimensions. So we've got B is a 3 by 100 matrix, C is a 100 by 5, and D is a 5 by 5 matrix. Now we've got a few ways that we could multiply them. So we've got B times C times D. Now, matrix multiplication is associative. That means we can group them in any way and we don't change the value. So multiplying all these operations together, this is the same as if we were to multiply B times C first, figure out what that resulting matrix is, and then multiply that matrix by D. And this is also the same as if we were to instead multiply C times D together first, and then take whatever that resulting matrix is and multiply it with B. So this matrix multiplication is associative. We're allowed to group matrices any way that we want, and we'll still get the same value. So we want to group them in such a way that results in the least number of scalar operations. But it's not commutative. So for example, B times C is not the same as C times B. So we can't change, kind of move one matrix to a different side. We won't end up with the same product, but we can group them in any way we want, and this is what we're going to do. We're going to figure out what's the best way in which we can group these operations so that we know, in this case, we multiply B times C together first, and then after we do that, we multiply the resulting matrix with D. So we want to find the best parenthesization, and this is our matrix chain product. So if we have these three matrices, we could just figure out the two different ways in which we could multiply them together, how we could parenthesize them. Either we multiply B times C together first, or we multiply C times D together first, and then count up how many scalar operations it takes in either case. Well, in the first case, we have however much it cost us to multiply B times C. Now, B and C, this will be a product of their dimensions, so this is, let's put it, we'll put it here. This is 3 times 100 times 5. This is how we get 1500, plus, now that we have B times C, how much does it cost to multiply this larger matrix, which is now a 3 by 5 matrix, just the product of these two matrices? How much does it cost to multiply this new matrix with D? And this will be, again, the product of their dimensions. So 3 times 5 times 5. And what we get is, whoops, this is a 5. What we get is 1,500 some operations. If we were to multiply them this way instead, and let me write down their dimensions here so maybe this is easier to see what they are. So we've got the following matrices. In order to multiply C times D together, this is going to require 100 times 5 times 5 operations. And then we have our resulting matrix is a 100 by 5 matrix. And in order to multiply that with B, this will take 3 times 100 times 5. So we end up getting something which is larger. This requires 4,000 operations. We're going to get the same value in both of these instances, but one of them required less operations. So definitely we want to group this in such a way where we don't have as many operations that we have to perform. Okay, so how could we approach this? Because this is an optimization problem. We want to minimize the number of operations. And we've already seen one design paradigm which typically works on optimization problems, which is the greedy method. So let's try to use the tools that we already have to solve this problem. Let's see what would happen if we tried to use a greedy approach. Well, there's a few greedy choices that we could make. Maybe we choose to, of all of the possible ways that we could choose to, let's say, multiply the first two matrices together, because we have to figure out what's the first operation we're going to do. Of all the different ways we could multiply two matrices together, we always grab the one that uses up the most operations. So for example, given these four matrices, we would choose to, between multiplying A and B together, or B and C, or C and D together, we would choose to multiply A and B together first, because we end up using up the most operations. We have that the smaller numbers are the middle common sizes. And similarly, we would multiply C and D together. Again, middle numbers here are the smallest, so we're kind of using those up in some way. This is just one idea of how possibly we could optimize how many scalar operations we perform. Then once we multiply them together, we only have one option left, which is to multiply the results. So we have 2,000 operations that we end up performing. But this isn't an optimal solution, because there's an even better way that we could have multiplied them, which didn't follow our greedy choice and gives us significantly less operations. So this would not be a good approach. But maybe we just picked the wrong greedy choice. Why would we want to use up more operations? Maybe we should try and use up the least number of operations. So we'll try again. Instead, we're going to pick, of all the choices we could make, which two matrices to multiply together next. Two consecutive matrices. We're going to pick the one that uses the least number of operations. So we'll calculate for each one of these how many operations would it take to multiply these two matrices together, and pick the one that uses the least. And in this case it would be B times C. This uses 9,000 some operations. And then now that we've formed this as one large matrix, we have to choose, should we multiply A with it first, or should we multiply it with D first? And we'll compare, of those two options, what should we do? And it turns out if we multiply it with D, that'll give us the least number of operations. So we'll choose that one, and then we'll multiply it with A. So this is the number of scalar operations we would need in order to multiply all of those together. This is just the product of those dimensions. So we get here, this is multiplying B times C together. This is 11 times 9 times 100. Now that we have this matrix, this is an 11 by 100 matrix, and D is a 100 by 99 matrix. So how we get the next number here, this is a product of those dimensions. So we've got 11 times 100 times 99. And now that we have this matrix here, this is an 11 by 99 matrix, and we're multiplying that with A, which is 101 by 11. So how we got this first number was a product of those dimensions again. 100 times 11 times 99. And we add them together because we had to do each of these matrix multiplications. Okay, so we end up getting quite a lot of scalar operations, over 200,000, using our greedy choice. But as it turns out, that is not an optimal solution. There's an even better solution we could have come up with, which uses less operations, which means that our greedy choice here isn't good. This will not lead us to an optimal solution. So we don't have a greedy approach, a greedy way of solving this. So we need a different approach. We need a new way of solving this.